Good morning, everybody. In AP Land today, we are going to talk more about entropy and the second law of thermodynamics. If you recall, the first law of thermodynamics said that all of the energy in the universe remains constant. And so the energy cannot be created nor destroyed, just like the law of conservation of matter, and the second law of thermodynamics follows suit. Well, now the second law of thermodynamics is that all spontaneous processes increase the entropy in the universe. So we're not talking about anything remaining constant anymore. So the universe and the energy is conserved, but entropy is not. So in taking a look at this, we need to take a look at our change in entropy in our universe. Remember, we are always talking about the system and the surroundings, and they are going to happen in pairs. And we are, in the chemistry world, always going to be the system. Remember, if you are looking at burning a piece of wood, you are the piece of wood. If you are adding sodium hydroxide pellets to water, you are the sodium hydroxide pellets. You are going to be the system. So if I have zero entropy, meaning my change in entropy is not changing, I am at equilibrium. And if you recall, the example that I keep using for equilibrium is our Hastings Bridge. Remember, we talked about that if 2,500 cars come across the bridge in the morning, those 2,500 cars maybe leave to go back home. It doesn't mean that there isn't busyness on the bridge. It just means that you have the same change happening in the forward and the reverse direction. So as I have positive change in entropy in the universe, I have many spontaneous reactions that are happening. If I have negative entropy in the universe, then I have fewer possible positions, probably something that's in the liquid or solid phase. Now if I take a look at the next section, we need to take a look at temperature. Is temperature going to play a part? And the answer is absolutely. So again, I have my change in the universe. I have to look at the system and the surroundings. If I have liquid water here, I can take a look that 1 mole of liquid water is going to take up 18 milliliters of space. So the molecules are moving around, but then we heat it up and we go to the gaseous phase, and this is going to take up 31 liters, that's not a typo there, of space, which, as you guys know, is going to be equal to 31,000 milliliters of space. So we have more positional probability here, we have a lot more space for these gases, we have an increase in entropy. All right, so now if we talk about our change in entropy of the surroundings, changes the surroundings that determine to the flow of energy. And we talked about the flow of energy of either being endothermic or exothermic. And we talked about that this exothermic is a negative change in heat, is how we show that. Endothermic is going to be the positive change in heat. You need to make sure that you keep these signs straight. Negative change in enthalpy means that you have a positive change in entropy, so meaning that we have more disorder, and opposite is true in the different condition. So as we take a look at this, how does this happen? Well, if you can think about some sort of system, it doesn't matter what it is. All right, let's say I have a beaker of something, okay, and this is going to be my system inside of here. Well, if this system is going to be releasing heat, all right, and this is my system and all this around here is the surroundings, does it make sense that if I'm releasing heat out here, that this is going to create disorder out here? And so that exothermic release of heat creates more entropy for the surroundings. And then the reverse is going to be true. If I have another system, actually this would be the surroundings, and I have my system inside of here, and I'm taking a look at that if I have energy coming into here, yes, I might be creating more differences here, but we are taking a look at the surroundings. So if I'm taking energy away from the surroundings, these molecules are going to move slower. I have less propositional probability, and so the change in entropy is going to decrease in the surroundings. Now, if I apply this to water, you can see that it is going to make a difference on the temperature. So what is the change in the universe? Well, we have to look at temperature. Think about our good old example of water always. Well, if I'm above 100 degrees, it's going to change from a liquid to a gas. Well, that should make sense to you that I'm going to create positive entropy. If I'm below 100 degrees Celsius, I'm going to be taking something from the gaseous phase to a liquid. I'm going to be condensing it. I have less positional probability here, So that means my change in entropy is going to be negative. So again, it is caused by the heat flow. Another example that your book uses is if I have $50. All right, I'm going to take that $50 and give it to a millionaire. Well, they're really going to say that's really not a big deal. They don't really need anything. It's not going to change anything. So the universe isn't really changed at all. But if I take and give $50 to you, that's going to be a great increase of entropy and more energy flow, because $50 to you means a heck of a lot more than it does to a millionaire. The same thing if I take 50 joules of energy. If I take 50 joules of energy and apply it to a hot tub that already has, really, really hot water, it's nearing, it's very, very hot. There's already a lot of energy there. The molecules are moving very, very rapidly already. Adding another 50 joules isn't going to matter. But if I take cold water that maybe you put on a pan of water on your stove, adding 50 joules of hot water to that is definitely going to change the entropy. So it determines its heat flow, and you have to think about the situation in terms of figuring that out. So entropy changes in the surroundings are primarily determined by heat flow. So you need to think about the phase of the matter and what situation that it is in. Entropy, exothermic reactions tend to increase entropy, even though there's a decrease in the system. So we are talking about mainly trying to figure out what's happening in the universe is focusing on the surroundings. The magnitude of the change in entropy of the surroundings depends on the temperature at which the heat is transferred. Again, back to that 50 joules of energy, whether it's already going into a very, very high temperature or low temperature is going to make a difference. And that's what's going to be shown here in this little formula. If I say that my change in entropy of the surroundings, this is a negative value of my change in enthalpy over the temperature. Again, all the temperatures must be in Kelvin. Well, if I think about that, if I have my change in heat as a negative value because I have an exothermic reaction, this negative times this negative, no matter what temperature you have here, is going to give you a positive change in your surroundings, a positive entropy. So then that means I'm going to have a spontaneous reaction. Conversely, we have to determine at the temperature what is going to happen. If I have endothermic and I put that value in here, I'm going to have a decrease in entropy in my surroundings. So the magnitude really does determine whether or not what kind of temperature I have. And we'll be taking a look at that in our example problems here. So what you guys can do now is, this is the end of this section right here, and the problems that you can do now in your book are in chapter 16, problem number 9, 19, 24, 33, 34, and 43. And placing more emphasis on these two right here that you need to know forward and backwards. So those are the ones that we'll be working on in class. And make sure you bring any questions that you have to class for me, and I'll be happy to answer them. Have an excellent day.